It's my pleasure to introduce Tuguldur Sukhbold. Tuguldur, or T as we like to call him, was an undergrad at University of Arizona. Got his PhD with Stan Woosley at UC Santa Cruz. Were you the last student with Stan?
That's my understanding.
That's all right.
You might have secret students.
And then from there, he went on to Ohio State. He was a CCAT fellow, and just recently, he was named a Hubble fellow. So in addition to all the great science Tug does, he also does a lot of great outreach, including he's brought telescopes back to his homeland of Mongolia and other great stuff. So feel free to ask him about that. He's going to be around. Today we're going out to dinner, so let me know if you're interested in going to dinner with us, but then also all day tomorrow as well. So there's still a few slots left in the schedule, so take it away.
All right, thank you so much, and thanks everyone for coming, and thanks for the invitation. It's really nice to escape the cold and windy Ohio, even if it's just for a couple of days. So I've been just standing outside and enjoying the sun for a while. And so today I'll be talking about my work on the lives and deaths of massive stars, and a lot of which were done in collaboration with these scientists listed here alphabetically. And they span across the globe from Monash University in Australia, Max Planck Institute in Germany, Ohio State, where I am now, University of Arizona, and University of California, Santa Cruz. Now, I imagine we all know why we care about massive stars, right? And despite their numbers, they play disproportionately important roles in the dynamical and chemical evolution of the galaxies. For one thing, they're the main source of the ionizing radiation in the universe. They're responsible for much of the heavy element nucleosynthesis, and their explosions enrich and steer the interstellar medium. And when they explode and die, they create some of the most exotic objects that we know in the universe, the neutron stars and black holes. So it's really important to understand the evolution and explosion of these stars. And a lot of what I will talk today will revolve around this newly emerging idea, which we call hypothesis of islands. And just to illustrate that here, I'm just simply plotting the initial mass space increasing that way. So on the bottom end, I have about 8 solar masses. It's about the smallest mass that so that the star would be considered as a massive star. So it's the smallest possible massive star. And I'm simply mapping which stars explode in green and which stars implode in black. And so there was this sort of conventional notion for a long time that basically said the difficulty of exploding a star cleanly scales with initial mass. So the stars at the lowest end would be very easy to explode, and as you go up, it becomes more difficult, more and more difficult, eventually reach some threshold right around 20 or 25 solar masses where you just can't explode anything more heavier. So all these stars would explode and create neutron stars, and all of these stars would implode and create stellar mass black holes. However, this new idea basically says maybe the reality is not so simple. And instead of this nice, clean separation, you might have a much more complicated landscape. So the idea is, the smallest stars would, again, be easier to explode. But as you go up, it becomes more and more uncertain. So notice that there's no clean separation of these two outcomes. Instead, you have islands of explosions in the mass range where you previously thought everything imploded. And also islands of implosions in the mass range where you previously thought everything exploded. And the main reason why we think this kind of more complicated explosion landscape may be more closer to reality is because, in general, the difficulty of exploding a massive star very strongly depends on the presupernova core structure. In other words, the structure in the star just before its death. And that core structure is known to vary non-monotonically with initial mass. So this talk is really about, just to briefly introduce you, the physics that carves this non-monotonic core structure as a function of initial mass, and what kind of explosion outcomes we expect from this kind of more complicated landscape, and what kind of maybe more future interesting observations that we could really use to distinguish whether this is more closer to nature. All right, before going further, let's do a very brief review on how actually massive stars evolve and die. And so here I'm showing what's known as the Kippenhahn diagram. Of course, it's a toy version. And on the y-axis, I have mass coordinates. So the center of the star here, surface here. And the x-axis, I have time. So the star is born here, and then the star dies here. And it's shaded different colors. These regions of different colors, shaded regions, denote the convective burning episodes of different fuels. Okay, so you see the star spends most of its life burning hydrogen in the center in a very massive convective core for millions of years. And then once hydrogen is finished, it goes on to burn helium in the center. While helium is burning, you have hydrogen burning in the shell. And then once helium is done, it goes on to carbon. And so on, it keeps burning heavier and heavier fuels until, of course, it forms this inert iron core, which you can't burn further for energy generation. And notice that because of this nested type of the evolution, the hydrogen burns in the center and then follows by a shell, and then helium same. It always carves out these nests within the star, and as you go burn the heavier in fuels. Because of this nested type of evolution, you carve out these regions inside the star from each major fuel that's devoid of its original composition. So we call these nested structures as cores. So for example, helium core is this part of the star, this part of its life, basically. Carbon-oxygen core is this part of the star, and this part of its life, and so on. So remember, the y-axis is the mass coordinate. So the outer boundary of this plot tracks the total mass of the star. So you see that during the main sequence evolution, while it's burning hydrogen, the star loses just a little bit of mass, mainly through the line-driven winds. But most of the mass loss, actually more than 90% of the mass loss, happens while the star is actually burning helium in the center. And globally, all the stars are born as blue supergiants. We call them compact blue supergiants, but these are actually very big stars. And it spends most of its life as a blue supergiant, but then coinciding with the ignition of the hydrogen in the shell, the outer envelope of the star expands and puffs up and cools down and becomes a red supergiant, which is about a factor of 10 times larger than a blue supergiant. And it stays as a red supergiant until its death. Now notice that the lightest two fuels kind of follow a simple path in terms of burning, right? So it burns in the central burning episode, in the convective region, and then follows by a shell burning episode. Same for the helium. It's a big convective episode followed by a shell. But starting with carbon, things get more complicated. And even what I'm showing you here is not a norm. Depending on the initial mass and composition of the star, you could have many more shells during this part of the evolution, or much fewer shells, or some fuels might burn in a radiative flame instead of a convective episode. And these shells could merge and split in the end. In general, this part of the evolution that happens in the carbon-oxygen core can be much more complicated. And we call this final part of the evolution that happens in the core as the advanced stages. And you notice that these nuclear burning timescales that I have on the bottom of each fuel, they get drastically short starting with the carbon burning. And this effect is essentially a consequence of the neutrino losses, which become very important starting with the carbon ignition. So here I have the neutrino losses for the corresponding evolutionary stages. And you see that starting with the ignition of carbon in the center, the amount of energy lost really shoots up. So the star basically loses massive amount of energy, and try to compensate it, it has to evolve really fast. And this really fast evolution in the center of the star creates a very interesting effect. So it's almost like this carbon-oxygen core evolves like a separate star. It's almost like a star within a star. Basically, the core doesn't care about what the envelope thinks, and the envelope doesn't feel what's going on in the core. And I think this effect is probably best described when we talk about actually a real star. So I know we have a lot of proper astronomers in the audience. I imagine everybody knows what is this, right? It's the constellation of the Orion. Okay, so we're interested in the brightest star of the Orion. It's a famous red supergiant star called Betelgeuse. And we think Betelgeuse had a birth mass around 15 to 20 times the mass of the sun. And the distance is about, I actually don't know, it's maybe like 500-600 light years away. So I know that a lot of people are interested, not just astronomers, but general audience interested to know when Betelgeuse is going to die. So you see, I hope you see that why this is a very difficult question to answer, right? Because when we see Betelgeuse, we see this puffy red supergiant. We see what's on the surface, and we have no idea what's going on in the core because the information doesn't effectively travel from the core to the surface. So the Kelvin-Helmholtz timescale, basically the timescale that's required for information to travel in the envelope, is on the order of many 10,000 years in this very puffy and tenuous envelope. But things change here on the order of 1,000 years. Basically, we have no way of seeing what's going on in the core. So, well, it's a red supergiant, so we know it's not burning hydrogen. Otherwise, it would have been a blue supergiant. So we know that it's burning one of these heavier fuels, but if it's burning helium right now, basically nothing's going to happen for the next 100,000 years. But if it's burning silicon, something will happen by next week. So basically, we just don't know. All right, now let's actually get back to more serious science. So the final inert iron core that is formed in the end will inevitably collapse. And this collapse can either lead to a successful explosion, or it might fail to do so and might result into an implosion. And people for a long time knew that this final fate, is this star going to explode or not, is really strongly dependent on the core structure right around this iron core. So the iron core here, the core structure right around the iron core. So to illustrate this point here, I'm showing the density profiles for stars of several stars of different initial masses. So it's the log of the density as a function of the interior mass. So I'm showing only the density profile in the innermost 4 solar masses. The surface of the star is way out there. It's just innermost 4 solar masses. So this means, this part right here in the very corner is essentially what's in the iron core. And what's outside the iron core is the surrounding silicon, oxygen, neon, and carbon-burning shells. And you see that for some stars, like especially the lighter stars, like 9 solar mass, this pink curve, the density is very high in the iron core, but then it drops down like a rock outside of the iron core. But then as you go look at higher mass stars, like this 40 solar mass star, this red curve, the density is very high in the iron core, and it stays very, very high outside the iron core. So in the old days, people knew, even though they knew not much about the actual mechanism of the explosion, which is still a kind of an open question even today, without even knowing anything about the actual mechanism of the explosion, they knew that these stars must be much more harder to explode than these ones. Why? Because there's so much matter in here. When the iron core collapses, there's going to be all of this stuff going to fall down on the proneutron star. The iron core collapses into a proneutron star. All of this is going to fall down. So to explode these stars, you need to overcome so much more ram pressure compared to these guys. So these guys must be much easier to explode than these ones. So one way of characterizing this final density core structure in the star before its collapse is what's called the compactness parameter, which is just the inverse of the radius enclosing a certain amount of mass. And that mass is usually taken as this innermost 2.5 solar masses, so it's like shown in this dashed line here. So as to basically sample not just what's in the iron core, but we want to sample the surrounding silicon, oxygen, carbon shells. So the idea is, when you have a density profile like this, and density is dropping down very steeply, you have to go far out to enclose a given mass because density is low. So when R is big, this parameter is very small. So this small parameter corresponds to things easier to explode. But then the opposite way, when you have a very extended density profile, you don't have to go far out to enclose the given mass. So this parameter in R is small, and this parameter is big, and that corresponds to things harder to explode. So when we calculate hundreds of actual stellar evolution models covering the whole initial mass range from 9 solar masses to 120 solar masses, and then evolve them all the way until this pre-supernova state just before the collapse, and then we compute for each model this final compactness parameter and put it as a function of birth mass, we get a picture like this. And as you can see, it's not a nice, smooth variation. Instead, you have this very highly non-monotonic with many peaks and valleys. And this is effectively the main reason why we expect a much more complicated landscape. Because these stars are generally easy to explode, but as you go up in mass, they become hard, easy again, hard again, easy again. So you just keep going up and down. So to understand the whole variation behind this, and of course we don't have time today, but I think in general one can build a working intuition by considering a few stellar physics, just to understand at least why we shouldn't expect a smooth, nice variation, why it should be these peaks and valleys. So
that's one definition of the compactness parameter. How much variation might you expect if you vary the definition a little bit? Like, would you kind of...
Right. So basically, by definition, you mean that the mass enclosed here, right? Or the time you define it. So one of the results of my 2014 paper was to show that, you can change this mass, you can change it to 1.7 or 3.5, and there's also this parameters defined. There's a question of where exactly defined, when it starts to collapse or in the middle of the collapse or it's actually started to collapse. And no matter what, the answer is the value of this parameter is going to change with the different m and different definition of the time, but this underlying pattern is going to stay intact. So the relative variation is going to stay intact. Mm-hmm.
To what extent does this general shape change depending on your assumptions about angular momentum of the star?
Okay, so I will mention that in the after 2 slides. Yes, but not in too much detail. But of course, I'll be happy to talk in more detail. So I said that briefly said that you could consider 2 input physics to understand why things have to be generally more complicated. And the first one is one has some idea what sets the initial composition of the carbon-oxygen core. So remember, the carbon-oxygen core is this part of the star. So we want to understand what sets the starting composition of the carbon-oxygen core. So that's set by, of course, core helium burning. But remember that helium is the only major source of fuel that burns in the star in the competition of 2 reactions, namely triple alpha that competes with carbon-12 alpha gamma. So triple alpha is a reaction that takes alpha particles, the helium atoms, and makes a carbon-12. But carbon-12 destroys the carbon-12 alpha gamma destroys the carbon-12 and makes it into oxygen. So the competition of these 2 reactions, you can see that sets the initial composition of the carbon-oxygen core, and it basically decides is it going to be more carbon-rich or more oxygen-rich. Now, because of their relative temperature dependence in massive stars, this reaction is almost always dominant. But again, because of the temperature dependence, as you go up in initial mass, this becomes even more dominant. So if you imagine looking at the composition of the resulting carbon and oxygen at the end of core helium burning, as you see in the stars of increasing initial mass, you're going to see that the starting composition is going to become less and less rich in carbon, but more and more rich in oxygen. And this has important consequences for the character of carbon burning, because to drive a convection, like as shown in this, schematic figure, to drive a strong convection, you need a lot of fuel. But when you don't have fuel, you're going to have a hard time to drive a convection, and ultimately your burning is going to shift to radiative flame instead of a convection. So to illustrate the point, here I'm showing on the bottom the same type of diagram, but only focusing on how carbon burning changes as you go up in initial mass. Okay, so as you go up in initial mass, just only showing you how things change in terms of carbon burning. So at lowest mass stars, this is still dominant, but still you have enough fuel to burn carbon convectively. So you're going to have a convective episode followed by shell burning. But as you go up to higher mass, it's going to become harder to burn convectively in the core, so your convective core essentially shrinks in size. And the following shells also going to shrink in their location too. But then ultimately you reach a point where you can't burn convectively at all. So the carbon instead burns radiatively in the center, and then it burns in the central region radiatively, and then once it can drive a convection, it starts the shells again. But as you keep going up to even higher masses, the more of the center part of the star carbon has to burn radiatively, and the shells seem to be migrating outwards. So you see that as just this nuclear physics playing during the core helium burning changes the character of the carbon burning, such that this carbon burning shells seems to be migrating inward and then suddenly deciding to migrating outward. And this varying location of this carbon shell burning has a very strong effect on how all the next fuel is going to burn. And just to demonstrate that, here I'm showing effect what we call as modulation. So it's the same type of figure. I'm sorry, I know you're all mostly observers, and this must be pretty dense, but I promise you this is the last of this kind of plot. So same type of plot, interior mass as a function of time. I arranged 3 of them in the same way that would describe what would happen inside a star of increasing initial mass. Now besides just carbon burning, now I'm showing what happens to the oxygen burning. And I'm also showing what's called the effective Chandrasekhar mass. So when we think about the electron degeneracy, we always think about white dwarfs. But remember that massive stars, in the cores of massive stars, especially during the advanced stage evolution, the degeneracy is also quite important, such that the effective Chandrasekhar mass has some approximate meaning. So the idea is, at low mass stars, there's convective carbon burning followed by shells, but the last carbon burning shell always burns within the effective Chandrasekhar mass. And therefore, the next fuel, which is oxygen, has to wait until the shell is completed. Because for the next fuel to burn, the core needs to contract and needs to heat up to really ignite the next fuel. But because this guy is burning inside the Chandrasekhar core, this material can't collapse and ignite oxygen. It has to wait until this is done. But as you go up in mass, the central burning becomes radiative, and all the shells start to migrate outward. And eventually you reach a initial mass point, where this last carbon burning shell now burns outside the effective Chandrasekhar core, effective Chandrasekhar mass. So now in this case, all this matter can actually collapse, and oxygen can ignite early on. without waiting until this guy is completed. But then when it burns early on, it has to burn in a smaller extent as compared to a lower mass model, because all this burning is actually relieving its pressure that it was supposed to support. So the oxygen burns as if it's actually burning inside a small star. And then eventually, even at higher mass, this guy will just keep going up and basically stop bothering how oxygen should burn, and the oxygen burning curve is going to increase in extent again. So you notice that as you go up in initial mass, this carbon burning character changes in the center, which then changes the location of the carbon burning shells, and then that modulates how the oxygen burning should go on. And this oxygen burning then changes how oxygen shell burning should go on, which then changes the silicon burning, and so on. Effectively, we have this kind of final crazy variation in the end. So over the past few years, we put out several papers, looking at the physics behind all of these variations. And beyond just the physics, we also put a lot of attention to understanding to all the uncertain input physics, so including convection physics. We don't understand how the mixing happens at the convective boundaries. There's also a question like he asked. There's the issue of the angular momentum transport in rotating stars. There's also the issue of mass loss. We don't have no physical understanding of the red supergiant mass loss. So et cetera. There are many issues. And so our verdict is that basically you change any of these important input physics, individual points will move around. Just like you change the definition of the compactness parameter. Individual points will always move around. However, this underlying pattern will stay very intact. So for example, if you imagine just calculating same hundreds of models, but with slightly different convection physics, all what's going to happen is all these points will just going to wiggle around, but these peaks and valleys are going to still be there, but maybe the peak going to happen at slightly lower mass or slightly higher mass. That's the only change there is. Otherwise, this underlying pattern is really driven by this modulation physics that I just very briefly and intensely described. But because of that, this pattern stays intact. So once we thought we understand how this underlying variation in the core structure comes about from stellar evolution, we want to understand the explosive outcomes. Now the interesting part comes. All right, now before going to how we did the explosions, go ahead.
Okay, one question. Can you go back just 2 slides?
Sure.
This is probably a pretty stupid question, but there's a lot of white space on these plots, and in this, it looks like the white space below a square is meaningful. There's really nothing happening there.
There's no burning in a sense. There's no strong burning. In a white space, you can think of a region where
It's just ash.
not just ash. White space are regions where neutrino losses are dominating the energy budget.
Okay. And is that true both above and below?
And below, yeah, it's all in the core, yes. And only in these convective regions where the nuclear energy generation from burning actually exceeds the neutrino losses. That's how you drive convection.
Okay. Thanks.
It's not a stupid question, actually. It's an important question. All right, so we surveyed the explosions in a very interesting, novel way. And before describing how we did it, let me just briefly say how people used to do explosions just until very recently. So the idea was that you just take these model stars and evolve until they're presupernova stage, so the center of the star here, surface here, and the idea is you just put in this arbitrary mascot, somewhere close to the center, and then you just deem that everything below this mascot is your compact remnant, neutron star or black hole, and everything above this mascot is your ejecta. And furthermore, they would put in a thermal bomb or a piston at this mascot, and then they would dial in energy, explosion energy. So they were basically controlling everything about how a star explodes. And in all these studies, they're looking at the nucleosynthesis and the compact object mass distributions, but they're really all just, like they had full control on how they do it. I'm not really criticizing, but this is just the way it was done for a long time. So we decided to give up all this crazy luxury and try to improve on it. So the way we improve is we take, again, a few presupernova models, actually 5 of them, that might be descriptive of these 2 relatively well-studied events, supernova 87A and supernova 1054, which is the Crab supernova, where we have some idea on the explosion energy and the synthesized nickel-56 masses in the explosions. So instead of this crazy mascot, we actually use a model that describes this collapse of the iron core into a proneutron star. So the idea is the iron core collapses into a proneutron star. It emits its binding energy neutrinos, and those neutrinos try to interact with this ejecta matter outside and tries to explode the star. And we actually compute the transport of these neutrinos through a gray scheme. So involving a lot of this complicated physics has some parameters, of course, and there's nothing to hide in there. And we tune those parameters using the observables of 87A and CRAT. So now the interesting part is once we have a calibrated, basically this tuned out and calibrated model, we then record how this boundary of this proneutron star contracts as a function of time. We record this boundary, which we call calibrated engines. And then we place these engines inside hundreds of other pre-supernova models. Instead of putting a mascot, dialing an energy, and telling it how everything should explode, we just put in these engines and then just sit back. So we don't control what's the remnant mass, what's the explosion energy, what's the nucleosynthesis. We don't even tell if you need to explode or not. We just put it in there and sit back. And when you do the explosions this way, you can have three types of outcomes, right? The whole thing might just be successful in driving a full-on explosion, and you might create a neutron star. Or on the other extreme, it might just fail to do so, and the whole thing might collapse and become a stellar mass black hole. And there also could be solutions in between, where it tries to drive a successful explosion, but the inner part of the ejecta collapses back onto the remnant, transforms the proneutron star into a black hole. So you could have a kind of a supernova explosion with a small mass black hole. And here are the results shown as a function of the initial mass. And as you can see, there's no clean separation of explosions and implosions. Instead, you have this much more complicated picture with islands of explosions here and islands of implosions at low mass. Go ahead.
Do you feel this diagram is converged in the sense that if you went to smaller mass cuts, there would be more little areas that might explode or implode, or is this basically completely the landscape's mapped out now?
So I see what you mean. It's not like, no, not like that. So for example, this is the plot from 2016, which had like 200 models between essentially 12 and 120 solar masses. And in 2018 paper, I had about 4,000 models between just right here. And the answer changed. But it's not because we have more models, but it's because we changed some input physics. We updated the input physics. But the general pattern, again, it stays roughly intact. Like you're not going to get more implosions just because you have more models in there. Or this island not going to get more narrow, more broad. It's still the same thing. Same physics drives everything.
So some of those slices, around 17 or 18
Yep.
are incredibly narrow.
Yep, and I will tell you about that. Yeah, in my -2, Python, the indentation is like my
Yes.
-1 slide. All right, the one before the. So the point of doing explosions, why would we bother doing like this? Why don't we just do the massive mass cuts and dial in explosion energies? Is because when you fully control the explosive outcomes, you can't really compare your models with the observations. But now we're doing this much more self-consistent approach, and this allows us to compare our models with all kinds of indirect observables. For example, the recent study by Muller et al. In 2017 looked at all of these successful explosions, basically all of these green bars, and took out the resulting explosion energies and synthesized nickel-56 masses, and compared with this beautifully determined observational correlation between these two parameters, and they found that our results seem to agree very well with what we see in nature. And we put a lot of emphasis on the compact objects resulted from our calculations. So in a recent study, they're done in collaboration with Frial Ozel of University of Arizona and her student Caroline Rathel. We basically first compiled all known masses of compact objects. So in this plot from our paper, on the y-axis, it's the masses of the gravitational masses of the compact objects of all known ones, and x-axis has no meaning, it's just arbitrary rearrangement. So basically you have all the neutron stars, known neutron star masses on the bottom, mostly between 1 and 2 solar masses, and all the black holes on top, mostly between above 5 solar masses and go on about until 60. And for the black holes, the actual masses that we use in our analysis are actually mostly these guys, which come from the X-ray binaries, from galactic and extragalactic ones. But we put these LIGO sources, connected with arrows, just for reference, even though we don't use in our analysis. And we find some very interesting results. So for the black holes, here shown the probability as a function of the probability distribution as a function of the black hole mass, and the observationally inferred distributions are this dashed and dotted black curves. Basically, the observations tell us that the black hole mass starts around 5 solar mass, peaks around 7 or 8, and then decays down until 12, 13. And our models, basically, I want to emphasize, they just right out of the box, without any tuning, they show this green curve. But I have to be honest, it's not like fully without tuning. There was one tuning involved, and the tuning was that we assumed in a final pre-supernova star, the envelope was somehow ejected. Only the helium core of the star imploded. And turns out, and we think that this is actually a much more physical mass, not because it's agreeing here, but because, imagine most stars are known to be massive stars in binaries, right? So binaries are very efficiently will strip the envelope from the other star. And that doesn't mean the envelopes are always stripped by a binary companion. It might have some residual envelope at the time of its collapse. But that residual envelope could be ejected during the collapse itself. Remember, the implosion, stellar implosion, is not like a magical process that turns a pre-supernova star into a black hole just like that. But it's actually, it still goes through this pro-neutron star phase. The iron core collapses, emits neutrinos. And we think this neutrino emission from the collapse can actually be just energetic enough to expel this loosely bound remaining envelope. So if you assume just the helium cores collapse into a massive star, it naturally produces a very nice fit. Now on the bottom, we have neutron stars. So observations seem to say that neutron stars show a double peak distribution. So almost all neutron stars, most of them show this distribution. By the way, x-axis is gravitational mass, peaked around 1.4 solar masses, and then there seems to be another small distribution peaked around roughly 1.8 solar mass. Now, these green points, they're truly out of the box, without absolutely any tuning, and they beautifully fit with this main distribution. Again, I keep emphasizing it's the most of the neutron stars, but I have to also be honest that this secondary peak seems to be not existent in our models. It's a little bit mystery, but I want to again emphasize that this is a highly debated feature. Observers don't everybody agree that this actually exists. So I don't know, but if this really exists, it would be a very interesting test. Go on.
I mean, the low mass peak is Chandra-Sekhar mass. Is that why it's there?
I mean, ultimately, yes, that's why it peaks there. But again, in massive stars, the actual iron core collapses not because of the it exceeds the Chandra-Sekhar mass, but it's not the one limit. You have to think of it in terms of effective Chandra-Sekhar mass.
I guess what I'm asking is that distribution the distribution of that number?
Of that number?
Of the effective Chandra-Sekhar mass?
Ultimately, yes.
Okay.
The physics is, it's ultimately related to that. But the interesting thing is if this is really true, something else going on. Go ahead.
Some of these are X-ray binaries that are accreting, right? So don't they have increased masses or is it not including?
Yeah, so X-ray binaries are for mostly black holes. Some of these pulsar measurements are also in binary pulsars. But the actual analysis on the accretion, again, I'm not an expert, but that's why I collaborated with Ferial Ozel, and she says, she told me I should trust her that these high mass stars are not because they accreted mass. They're actually born this way. Yeah. Go ahead.
So many questions. Here's my dumb question. Your predicted black hole masses, are they, because of your variation in core structure, are they completely or mostly uncorrelated with the initial mass of the star?
They're correlated with the initial mass of the star roughly until about 30 solar mass, from 8 to 30. And then after 30, because the mass loss effect becomes very strong, the correlation breaks down.
So does the shape of the observed distribution have some constraint on the shape of the initial mass for that mass range?
If our explosion landscape is correct, yes, that's very smart. Yes, if that landscape was true, then that would put a constraint. But then,
People would have to believe it, right?
I don't also believe in everything I do. So
I had a paper many years ago where we tried to invert the problem and say, okay, if this is the distribution of black holes, what's the IMF of these massive stars? But it's hard given the limited number of black holes and stuff.
All right, so beyond neutron stars, black holes, and explosion energies, nucleosynthesis, we also looked very closely at the overall global nucleosynthesis and found some very interesting stuff. Unfortunately, because of time constraints, I'm not going to talk about much of nucleosynthesis right now, but if anybody's interested on that side of things, I'd be happy to talk about those, and I'll be around tomorrow. But in a given time, I want to mention about two types of observations that could really help us in trying to decide if this is really the nature, how it works or not. So in my opinion, the most powerful type of observation is what's called a direct progenitor imaging, where on one side we have people searching for archival images of the progenitors, where you see a supernova, and then they see get another image after the supernova faded away, and then they look for archival image and a high-quality image before the supernova, and by subtracting the two, if they're lucky, they can get a flux of the actual star that exploded. And with the distance estimate, you can convert the flux into luminosity, and with some theory assumptions, you can convert the luminosity into a progenitor initial mass. But of course, this high-quality images, and again, I'm a theorist, I don't know much about, I'm just like telling you what I read in papers. High-quality images are apparently very rare. I guess that's how it is. So we have this kind of good quality measurements only about for like a few dozen supernovae. But when Stephen Smart puts these progenitors measurements for this type 2p, about 20 type 2p supernovae, he basically, in a small volume limited sample, he basically gets that the birth mass range of the type 2p supernovae roughly come from 8 to 20 solar masses. So when I translate that mass range into my landscape, basically it squarely falls on the range where I expect most stars to successfully explode. On the other side of the exercise, we have the opposite problem, people looking for disappearing stars instead of progenitors of exploding stars. And we only have one detection, and again, doing the same exercise game with the flux and mass, the estimated mass is thought to be somewhere between 20 and 26 solar masses. And again, putting that here, it falls in the range where I expect most stars should implode. But the problem is all of these measurements, even though this is amazing, and it's direct progenitor imaging, I think it's absolutely amazing, but all of what we have now is perfectly consistent with what I get. But it doesn't really constrain if it's, compared to the classical picture, which one is true or not. So I think because my models specifically predict this island at high mass, it'd be really interesting if direct imaging observes a high mass explosion from a red supergiant with mass about 26, 27, 28 solar masses. I mean, there are some indirect type of evidence of this kind of explosion exists in nature, but we don't have any direct imaging evidence. And also in the opposite direction, because we predict this implosion at low mass, stars as low as 15, 14, 16 solar masses. So if they find a star disappearing at 15, 14 solar mass, that would be a very strong evidence to say that this is the right picture. Go ahead.
I'll just add, because I'll forget if I don't say it now, that there was a paper within the last year that reanalyzed these and said that the masses were actually systematically slightly low because the limited HST bands were used.
Yes, yes.
So it actually matches even better with your theory than that diagram
Yes.
indicates.
Yes. Yeah. And another type of study, none of this published, it's just because I put it because you guys are all observers, is what I call Tailless Type II supernovae. Okay, and this is important because our models predict, one of the fundamental predictions of the model is that fallback explosions should be very rare in nature. They might not exist even at all. So, and the telltale signature of a fallback explosion is so-called the tailless Type IIp supernova. So the illustrator here, I'm showing the luminosity as a function of time, basically a light curve. And this background gray band basically describes the luminosity range, and there's basically range of all observed normal Type IIps. So in the Type IIps have essentially two main components, right? The plateau phase where the luminosity stays constant for 3 to 4 months as the shock deposited energy in the red supergiant envelope is slowly emitted through recombination. But as the recombination wave finishes going through all of the envelope, then the whole ejector transitions to nebular phase, and then the second, this nebular phase is exclusively powered by radioactive decay of cobalt-56 to iron-56. And this cobalt-56, of course, comes from the original nickel-56 that was synthesized in the explosion. So when the fallback explosions, remember, the star tries to have a normal explosion, but then the innermost of the ejecta falls back, and the innermost ejecta contains almost all of the exclusively this heavy stuff synthesized in the explosion. So all of this stuff that would have driven the tail is now all trapped in the compact remnant. So instead, the light curve, this is the actual model that I computed recently. So you're going to have a shock breakout, a plateau phase, just like a normal 2P. You wouldn't tell the difference. And then when it comes to this tail transition to the tail, there's not going to be any tail. It's just going to drop down. And from what I know, again, and I'm a theory guy, I don't know anything about observations, but from what I know, we have never observed this. This has never been cleanly observed. But I think there could be a bias issue because from what I understand, again, the observers, when they see Type 2P, they just make few measurements on the plateau phase, and they don't really bother to follow the actual tail. because but again, understand it becomes dim and probably expensive and not interesting. So, but I think if observers could do a more careful study on type 2P, if you could do, like, for example, a volume-limited study that could really, you focus on this, making measurements on the tail, and if you find that this kind of explosions actually do exist in nature, and they're actually quite common, and common such that it's more than a few % of all core collapse supernovae, then that would actually mean we're doing something very wrong with our explosion modeling. And this could be a very important observation. All right, do I have time?
Yeah, you guys have it.
Okay, so given in the last few minutes, I want to very briefly mention a very recent result looking at the question that some of you guys were just asking just about now. So in the explosion landscape, we have this range where the final outcomes are just shifting up and down, up and down. Stars are exploding, imploding, exploding, imploding for stars with nearly identical initial masses. So how is this possible? And we looked into this closely, and we find that the inward migration of the carbon-burning shells that actually makes the final core structure not just non-monotonic, but actually discontinuous with separate, distinct branches. It's almost like presupernova evolution is multi-valued. So it has this inherent stochasticity. So this plot from our figure, don't worry about the meaning of the y-axis. You can just think of it as a final core structure, proxy for the final core structure. Higher values mean stars difficult to explode, lower values easier to explode. And the x-axis is now shown as a function of helium core mass, but the corresponding initial mass is roughly between 14 and 20 solar mass, just in this red band, essentially. And you see that the final core structures are not just, non-monotonic, they're not just doing this crazy variation, but they're actually fully discontinuous. The evolutionary path follows one set of evolution, type of advanced stage evolution, the carbon-oxygen core, and then jumps to another family of solutions that follows a separate path of advanced stage evolution, the carbon-oxygen core, and then jumps to another final third branch. And so the implication is that, stars, we should expect totally nature in stars to almost twin stars, like almost identical initial mass, or identical mass, but just tiny difference in the composition. Or you could think of two models with just tiny difference in any kind of input physics. And we should expect them to have very different outcomes in certain ranges of initial mass. One star might explode and one might implode. Or even if both of them explode, it's very natural for them to have very different explosive outcomes. Different compact remnant masses, different explosion energies, and different nucleosynthesis, and also light curves, possibly too. All right, to summarize everything. So the main message I want you guys to take away is that the final explosion of a massive star, not until very recently, people thought that everything exploded, or they had these crazy simple pictures, but actually the final outcome is dependent on this final core structure, and that core structure varies non-monotonically with initial mass. And furthermore, it could be actually multivalued and stochastic in certain ranges of initial mass. So this means that I don't know if you guys heard about the Vogt-Russell theorem. It's not like an actual mathematical theorem per se, but it's a statement that says you give me a set of initial conditions in the mass and composition, and the equations describing the stellar structure and evolution guarantees you a well-defined and unique solution. But that certainly is not true for the pre-supernova evolution of massive stars. And the hypothesis of islands that I've been saying is broadly consistent with all kinds of indirect observables, and we can now first time really comparing with these observations, but we really need more observations to really say, is this how nature works, like this or this? And in the end, I'm not really like boasting our work, but it seems like our work kind of starting to put a new standard in our field, especially in the context of nucleosynthesis, because in several papers after our paper came out looking at the nucleosynthesis of massive stars, there's just 3 examples, there are actually 5 of them, and now all of them using some kind of explosion physics. I mean, they basically stopped doing this crazy mascot and dialed in energies, and they're not doing exactly the same thing as us, but they're at least trying to be more realistic, and I think that's a very good thing. And I want to mention that all of these calculations that I described, the pre-supernova models, explosion models, the nucleosynthesis yields, light curves, everything is freely available from my website. And this year I've been ending all of my talks with this beautiful quote from a 19th century German philosopher who said, "You must have chaos within you to give birth to a dancing star." Thank you very much.
So I suppose in the end, the final thing that really is intriguing is having these different branching outcomes. Yeah. And so there's clearly a lot of chaos driving the outcomes. And in the end, that presumably means you have to run many more sets of models
Absolutely.
of identical initial conditions. or
Absolutely.
slightly different, in order to just get that probabilistic
Exactly.
distribution at every mass.
So,
How much more work is that?
I mean, it's a lot of work, but you know, we're living in a day and age of very powerful computers, right? And these are not like the fancy 3D simulations that some of you see in other talks or in documentaries. And these are just spherically symmetric, beautiful, you know, simple. I mean, it's very complicated, but still, it's this beautiful simplicity in it, right? It's a very viable simulation. So the problem is, even now, a lot of these people, and I'm not saying this because I'm a younger person and, you know, saying this against older people, but it seems like a lot of these people are just evolving one star here, one star here, one star here, one star here, and then another star here, and then they're trying to make conclusions about evolution of massive stars, and it's just wrong. And one of the things they've been trying to say in the past few years is study of massive stellar evolution in some sense is almost like a statistical science. It's just like he said, we need to evolve in hundreds or thousands of models just to understand this underlying pattern. And going to this picture, the whole reason why we did this study was actually not to understand this, because there have been people started writing papers saying that, oh, now I varied mass loss and look at the final structure and oh, it changes this and that. But that means that mass loss is the most important thing. And then there's another paper just saying like, oh, I varied convection and then this happened. And then I varied rotation, this happened. So in this region, the physics that we learn is that it doesn't actually matter what you vary. You can vary the mass of the star. Mass, you just start in composition. And this is underlying physics is inherently stochastic. It doesn't care what you vary. So that's the kind of the message that we've been trying to convey. But what you said is, I completely agree. We have to do thousands or hundreds of them at least. And this is perfectly viable with given today's computers. You know, I use supercomputers, but I never use like this, you know, national level computers. With small university clusters are more than enough always for me.
So I guess, is there anything that you think you might be losing by not having the 3D calculations? Is there like anything that stands out to you as you would like to have included in these calculations if it was sufficiently cheap?
That's a very good and very difficult question to answer. Well, in terms of the science, the thing that I really miss about not having, you know, because, you know, a lot of this problem is, especially when it comes to collapse and explosion, is inherently multidimensional. One of the scientific part that I miss about is the actual kick of the compact remnants, you know, because it's spherically symmetric calculation, I can't really say anything, but these kicks are really important for a wide range of astrophysical phenomena. But in terms of our results, it's really, really hard for me to give you a definite answer because the actual mechanism of the explosion is such an open problem. You know, of course, you know, the problem is complicated, rich in physics, inherently multidimensional, but just think of it like, you know, there's no way for us to survey this kind of, get this kind of insight from three-dimensional studies, even in our lifetime. Our only way of approaching this problem is through these, you know, large surveys of 1D studies. Of course, you know, I give up some accuracy with the expense of computational time, you know, computational expense, but I gain the ability to probe very wide parameter space. And this type of study is extremely important when the systematic uncertainties of the actual explosion physics is not known.
Can you speak a little bit more to Dan's question about rotation?
Right, rotation, okay, I have a lot to say about rotation, but first of all, none of these models rotate, okay? Second of all, I don't think we fully understand rotation and angular momentum transport in the stars. So there's one model, very famous model that everybody's referred to now. It's actually from a 2005 study. And they basically predict that, yes, rotation affects things, but mostly due to rotationally induced mixing. So if you could imagine a 20 solar mass star that included some rotation would actually look like a 22 solar mass star with no rotation. So basically, things get more mixed up. The carbon-oxygen core, the helium cores are more massive in the rotating model versus non-rotating model. So that's the kind of basic verdict. They think it affects with more mixing. So if you imagine all of these models adding a rotation, you know, all of these bars going to just move to a slightly higher mass. Nothing else going to change. But basically, that's the verdict. But I don't think it's actually.
The rotation will induce an asymmetry.
Oh, that depends on how fast you're rotating. With the given observed speeds, that's not the case. And remember, when a star becomes a red supergiant and everything is so puffs up, the radius is like, a few times 10 to the almost 14 centimeters. It's extremely large star. So you're not going to see much any sphericity effect on the red supergiant.
Even in the core?
In the core, so that would depend on the coupling of the core and the envelope. So with the current understanding, there's not going to be, they're actually going to be strongly coupled so that it loses a lot of angular momentum in this expansion, so the core actually slows down.
Time scale, the dynamical time scale for the core and the envelope is different, right? So will we lose?
But yes, dynamical time scale for information to travel in the already expanded envelope is very large. But the expansion itself happens also very quickly. From a blue supergiant to red supergiant happens very quickly.
I think you said that a large fraction of the energy transport is through neutrino emission.
Yes, sir. Mm-hmm.
So that would seem to me to suggest that rotation is not going to be that significant. Because basically they pass out fairly spherically, symmetrically out through them.
That's the idea. I mean, we see supernova explosions, the typical energy is 10 to the 51 ergs. The amount of energy that's released by the binding energy from this collapse emitted neutrinos in 10 to the 53 ergs, and 100 times more. So the neutrinos, of course, don't strongly interact with matter, but if it's just 1% of it interacts with matter, that's enough to explode the star. But the problem is when you actually put in all this physics into the so-called, first principle, all the fancy, bells and whistles, 3D simulation, it doesn't actually work. So some people don't think neutrinos explode the star. Maybe actually rotation actually plays a role in there. So it's an open problem right now. But if neutrinos really drove the explosion, that would in some way suggest that rotation, asymmetry from rotation is not very important.
Really thinking in terms of driving the explosion.
Yes.
At more its evolutionary point of view. If it's rotating, that will distort the effective equipotentials from the thermal, the temperature gradient.
Okay, I see what you. But that would mean actually still that's a very strong rotation to really affect that kind of level. I mean, the amount of rotation that we predict from the collapse of the iron core with the current models is not very much. I mean,
The effect of that would be small.
Yeah.
If you have a lot of neutrino transport.
So I have one question. You go back one slide. I think it's one of the striking things is, well, my question is about like nucleosynthetic signatures of this.
Yes.
In particular, focusing on the 20 to 30
Yes.
solar mass range where there's this large explosion regime there. Unfortunately, Andy McWilliam isn't here, but he would be able to comment on this better than me. Maybe we could talk about it with him tomorrow. But there's large variations in the oxygen production across 20 to 30 solar
Yep.
masses. And I could imagine the nucleosynthetic output's very different for this compared to the
The
story.
full. Yep. Yeah.
So
Yeah.
Could you comment on that? Or?
Yes, but actually it's not going to be in oxygen. I knew somebody might ask this, so I actually brought nucleosynthesis plot. I'm going to be real quick on it. So this is actually taking all of the successful explosions, taking the yields from successful explosions. But the implosions also contribute to some level to the explosion because the stars lose mass, either through stripped by a companion or through normal mass loss. So all that mass will also contribute to the yields. So we take all of these contributions, fold it into initial mass function, and then we compare with the solar abundances here, essentially, okay? And everything normalized to oxygen. So what we see in the sun is essentially this orange band, and everything else created resulting from this IMF faulting is all this blue dots. So you notice that some things fall into the band, some things don't fall, but again, we don't expect massive stars to be responsible for everything. For example, the lightest elements, they come from Big Bang nucleosynthesis, so we don't care if massive stars are responsible. There's like beryllium here, way off axis, created by cosmic ray spallation, for example. But then notice the elements here that are deficient. Again, we don't worry about it because it's called the iron peak, because most of the iron in the universe comes from thermonuclear explosions of white dwarfs. But the interesting thing we found is this part. This is so-called the weak S-process elements. These are neutron capture elements that we thought, everybody had no question that these elements are created in massive stars and actually yielded, comes in their yields. But now once we give up that luxury, if you assume everything exploded, all these points will just fall in the yellow band. But now because we give up that luxury, and now many stars that were producing all of these elements are now imploding instead. Now we start to have this deficiency. So there's no question that these elements are created in the stars. That nuclear physics is so extremely well established. But just because, the fact that you contribute to the yield is not about how much you make it. You actually have to explode and put it out into space. If you don't explode, you don't really contribute, even though no matter how much you make in the star. So this is probably the most important aspect that we found from this kind of landscape. And so this means either we're missing something, possibly rotation. So we think that these stars, exploding stars, when you add rotation, when you add this extra mixing, you can actually create a lot of these more elements. So even with this deficient, more complicated landscape, you can still make it match to the band, for example, with adding more rotation or updated nuclear physics. But it's also possible that these elements are actually maybe not made in massive stars. So it's an intriguing possibility. I think it's highly unlikely, but I think it's maybe worth thinking about it.
But you showed it's such a nonlinear process that is it conceivable that it's really just a small change in the window of implosion versus explosion in that mass range?
Could fix it? No, it's impossible.
It has to be a big change?
It has to be, it has to be. So if you make even all of these stars explode, still you're not going to fix this. It has to be a very significant change. Thank you very much.